Hello, class. I am going to record another lecture, and this will be the final lecture. In fact, we'll probably get on to a little bit further, talking about various different things as far as charge and capacitance and some other things, just as far as the units go, of course. But then we're going to start to look at Ohm's law and things like that. We'll see how far we can get. I should grab, there is my phone. I could set my timer up. Not that we ever really get to the end of the timer. Oops, wait. Let's do, there we go, start. All right. Today, yeah, I'm going to finish up on dimensions units. I want to talk about a couple units that are of particular interest, and your conceptual understanding of these units is something that's going to help you all throughout your engineering education and throughout your life and your professional career too. So let's talk about the units that we got up to. Now, we did get up to power. We've done resistance. We've done voltage. And so we had all of those in our last lecture. What I want to do now is I want to talk a little bit about charge. And so when we think about charge, usually charge is represented as Q. Sometimes a large Q, sometimes a small Q, but it's usually represented as Q. And you might have remembered me saying in lecture 1 that had I been back there at the convention on the units, the System International in Paris, I would have probably voted to go with charge rather than current as my, just a second, let me just, I hope I'm recording this. Yes, I am, just a second. Yeah, I just wanted to get a bottle of water. So anyway, charge, and we know that charge is in coulombs, right? Now, is charge just like water flowing through pipes? Is that what charge is like? Yes. I mean, in the most simplistic look, it is. But here's how I want you to think about charge, because all the charge that we're using in, electromagnetic, in the electromagnetic force, and using electrons to charge things and everything else, we're using electrons, aren't we? And in fact, the electrons are so important that we should write Q to the E, and notice I've put a minus sign there because, of course, the charge on an electron is negative, minus 1.602 times 10 to the minus 19 coulombs per 1 electron. Notice how I put coulombs per electron. That is what the charge on one single electron is, right? Now, let's write that up there, because that is something you're going to commit to memory. Commit that to memory for the rest of your life. You're an electrical engineer. You really should know what the charge on an electron is. In fact, you should probably know what the mass of an electron is, because an electron is your life, isn't it? Now, I remember this, and every other electrical engineer that you'll ever meet in your entire life will be able to tell you what the mass of an electron is. You're not there yet, right? You're still a couple years away from joining that club, but it is 9.1 times 10 to the minus 31 kilograms. All right? So those two things you really should know. You should also take away from here the fact that pi is 3.14159, and let's not forget that Euler's constant, and I mentioned this in the last thing too, is 2.71828, right? So take that away with you, and you're probably way ahead of me guessing what I'm going to ask you to do next. And if we know now let's just look at this for a second. So I know that one electron is minus 1.602 times 10 to the minus 19 coulombs, right? So then the next question is, if I had a bucket of electrons, and inside that bucket was 1 coulomb's worth of electrons, right? We've got a bunch of electrons trying to escape here out of my electron bucket, right? So I've got a bunch of electrons. How many electrons do I have in that bucket? Right? Think about it. How would I figure out if I had minus 1.602 times 10 to the minus 19 coulombs per electron, how many electrons would I have in 1 coulomb? And I'm sure that you're saying, okay, God, you know, his units there, coulombs per electron, if I just reciprocated that, I'd have electrons per coulomb, right? If I just took the reciprocal of 1.602 times 10 to the minus 19, I would get 6.24, 6.24 times 10 to the 18 electrons per coulomb. See how I did that? And I'm sure that many of you did exactly the same thing in your head, and you immediately knew what I was doing. Those of you who didn't, catch up. No, I'm kidding. It's not really catching up. You're going to be homogenized throughout the course of your engineering education. That's just how it works, because you know, some people have already had some of this stuff. So in your freshman year, and even in the beginning of your sophomore year, when you're getting into your first technical courses, you may not be homogenized. There may be some people with more high school experience than other people, and they may be ahead. That's good, because you know, sometimes you can keep that momentum going, but then other times there's things that happen in your life that tend to throw you a curveball. That's right. I'm sure that some of you can intimately agree with that. So that's what you want to do. Let's just get all of this together. So that's the amount of coulombs. Now, what if I had a very short piece of wire, right? And around that wire I had some well, I think I'm going to have to draw this first. Let's see. There we go. I'll draw it like that. How about that? And then that goes around there. Oh my God, it's starting to actually look like a wire. Don't tell any art teacher. There you go. So let's say that I've got a piece of wire. It's about 3 inches long. From one end of the wire to the other end of the wire, it's going to be 3 inches. This is something that will be counterintuitive to your understanding, but believe me, I'm going to explain it. Now, also, remember, we've got this cross section here, and let's say that I have plus 1 volt on this end of that 3-inch wire, and on the other end, I've got 0 volts, right? Now, let's say that the wire itself, if I was looking at a schematic of the wire, I have a 1 ohm resistor, right? That wire is got like 1 ohm of resistance in it, right? Hardly any resistance. Now, that would be a lot more resistance than a 3-inch wire. I'm going to tell you that right now, because a 3-inch wire would have close to 0. But let's say that we haven't made this wire out of aluminum, and we haven't made this wire out of copper. Now, you're probably saying, hey, you know, why, let's say we made it out of metal, right? So it's a wire. Schematically, I've drawn it as 1 ohm. And we've got it. Now, with Ohm's law, V equals IR, and some of you may be familiar with that from high school. From Ohm's law, that then tells us that the current that's going to be flowing through that wire would be 1 amp, right? because I would be voltage, 1 volt, divided by R, which is 1 ohm. That would give us 1 amp. So I would have current flowing through that wire. And of course, we know that current flows from the positive to the negative, right? So I'd have current flowing through that wire from the positive to the negative. Of course, electrons, by the way, go in the opposite direction. I'm just going to point that out to you. So electrons, they go from negative to positive, right? So if we were looking at electron flow, it would be flowing in that direction. But the current, I, is flowing in the positive to negative direction. I'm sure everybody, understands that. I just thought that I'd point out that electron flow, because it's a negative charge carrier, is going to be going in the opposite direction to the current, which we've defined as going from positive to negative. And of course, we did that because we didn't know. At the time that we defined current, we had no concept of charge and everything else. And of course, charge carriers are electrons, and that's what we've got. So that's quite a bit that we've got there. Now, if that's 1 amp, right? Now 1 amp, 1 coulomb. If I have a wire, let me just draw this. If I have a wire and I have current flowing through that wire, right? I have my current is 1 amp of current flowing through that wire. And I flow the current through that wire for 1 second. I flow the current through that wire for 1 second. 1 amp for 1 second. That will transmit 1 coulomb of charge. 1 amp flowing through a wire for 1 second transmits 1 coulomb, or 6.24 times 10 to the 18 electrons. Isn't that incredible? 6.24 times 10 to the 18 electrons transfer through a wire that's got 1 amp for 1 second. So what we can say, since we know that an amp is current, right? So we can say that 1 amp equals 1 coulomb per second. That's supposed to be a C. 1 coulomb per second. God, it doesn't look like a C, does it? I'm going to write it again. 1 coulomb per second equals 1 amp. Now you could say, okay, well, we could say that it's 1 coulomb per second, or we could say that 1 coulomb equals 1 amp second. Notice I've got the dot there. It's not amp per second. Of course it's not. Look at the math. Look at the algebra that we've got here. 1 coulomb equals 1 amp second, and that would mean amp for 1 second gives me 1 coulomb of charge. That gives me 1 bucket, or 6.24 times 10 to the 18 electrons in 1 second. 1 coulomb. All right, does everyone understand that about that? Now, I want to also point out, what if I was to put this, and I had this set up as, and I just threw a switch, right? How long would it take an electron that goes in one end of this 3-inch wire to get to the other end? Let's say that I colored the electron that's going in this end, right? I made it orange. So I stick an orange electron in one end here. How long does it take to get out the other end of a 3-inch wire? You're probably saying, oh, it's got to be the speed of light. No. What this electron does is it goes into the crystal lattice that's in the copper. It knocks an electron out of an atom there. And then that electron starts going and hits another electron in another atom, and it knocks an electron out of there, right? And so although as soon as I throw the switch, the electronic pressure, just like your shower, right? As soon as you turn on your shower, you don't have water from the reservoir immediately come into your house. No, you have water that's been in the piping system for 7 days that's coming into your house. But as soon as you turn that faucet on, the pressure, the water pressure pushes that water that's been in the pipes for 7 days out onto your face. I know, all of you are thinking, oh my God, what have I been doing? That's right. What have you been doing? But it takes about an hour. It would take about an hour for this particular orange electron that I tagged to knock other electrons free and to keep moving down and to, it would take about an hour for it to actually get out the other end, right? So I'm just going to put him here. I want you to think about that. And of course, think about the fact of what I'm really saying is that just like in the water main system of the city, there's a lot of water in that water main system. And when you turn the tap on, there may be more water that flows from the water tower into the system, the plumbing system, but the pressure in that plumbing system is immediate. In fact, it travels at the speed of sound in water, if you really had to know, but that's pretty much instantaneous for us. The same thing's true here. As soon as I throw that switch at 7/10 the speed of light, I start getting, the current flowing through here, but that one electron is going to take a long time to actually get through that wire to the other end because there's already so many electrons on the inside that it has to push out before it gets to the other end. I hope that I made that clear. I love to try to, make people realize things that are counterintuitive to what they may have learned prior to this. Anyway, so now that we have charge out of the way and an understanding of charge, electronic charge out of the way, let's look at what that gives us in some ways. What is capacitance? Capacitance is just charge divided by voltage. Charge divided by voltage. And what really is a capacitor? I'm just gonna draw the capacitor for you, and I want to discuss a capacitor for just a second, sort of in general terms. I'm sure that some of you have had some familiarization with capacitors, maybe in high school or whatever. So let's say that I've got about 100 volts on this side, and I've got, well, we'll call this side ground, right? And in fact, how would I hitch that up? I would just run this down to a battery, right? That's a 100-volt battery, 100 volts battery, and then I would just run this over to, well, I could run that to ground, and then everything here to here is really just excuse me, is really just a short circuit. So I've got this set up like that. Now, what's in the middle, right? So right now, I'm really saying that this plate over here is 0 volts, right? Well, that doesn't come through too well. This plate over here is 0 volts, all right? And then the plate on the other side is 100 volts. So let's just blow that up in 2 dimensions to see what I've actually got there. I'm just gonna blow this up. In fact, I guess I could make it, it's going off this way, and that's going off this way. But what's in the middle of that? It's an insulator. Yeah, that's right. Don't ever think that there is one electron that is going from one side of that capacitor plate, right? So this is a charged plate. And this has a charged plate over here. They both have a charge, equal and opposite charges on both sides of those 2 plates, just like I've drawn there. But what's in the middle of those two plates? They never touch. In a capacitor, the plates never touch. I want to point that out. I hope this works, because that looks like a nice, oh no, of course it doesn't, because they all hate me, all of these pens. What do I got here? Oh, that's brown. Oh yeah, we'll use brown. Yep, barium strontium titanate, which is brown, actually. I mean, I know that because I ripped these apart and, you know. So I've got barium strontium titanate, which is a fantastic dielectric and is an insulator in the middle of this capacitor now. And I'm charging the two plates. Now, what happens to the current? Let's say that instead of having this like this, so that it's all connected, that I actually have a switch. I'm just going to put a little switch in here, right? And I can throw that switch. Now, the capacitor is uncharged to begin with, so I don't have any positive charges here, any negative charges here, right? In fact, the dielectric itself is unpolarized, and that's what happens to the dielectric inside. It starts to get polarized where its negative charges go to one side and its positive charges go to the other side, right? So when I throw that switch, and in fact, I'm going to put a plus on here just to let everybody know that that's a positive. Now, what attracts to the positive? Isn't it the negative? Once I throw that switch, aren't all of the negative, or in the beginning, it's going to take a little while, but aren't the negative charges going to start to align over here? Isn't that what happens? So that I'm getting more and more negative charges over here. Hey, what's going on at the other end? Right? Because this is the negative over here. So this is my negative. In fact, instead of making that 0, why don't I make it negative 100 volts so that it really in your mind just, you know, sticks there. So I've got minus 100 volts on the other side connected to this thing right here. So I've got minus. And so what's that going to attract in the dielectric? That's going to attract a lot of positive charges in the dielectric to line up here, right? So there's never an electron that ever transfers through a capacitor. Now, the next thing I want to ask is, once I throw this thing, is there going to be current flow? Oh, you know there is. Oh, yes, absolutely. The charges in here are going to start to move in that direction. So as soon as I throw it, we're going to have these charges lining up, and for them lining up, that's going to change what the polarity is in the things right here, in the electrons within the wires. So the electrons within the wires, well, that's positive, right? So what's going to happen? The electron that's in the wire here, let's make the wire a little bit larger and make it look like a pipe. Because isn't it really a pipe for electrons? So now on the plate here, the plate is going to be positive. And where are the electrons going to go, right? Aren't the electrons going to be attracted to the positive side of the capacitor? See what I'm trying to do for you here? I'm trying to teach you. Now, how about the electrons in the wire over on this side? I'm using the wrong color there. So I've got another wire over here on the other side. How about the electrons in that wire? Aren't they going to be pushed away from this? And they're going to start to go in this direction? So we've got wires that are flowing, electrons that are flowing in that direction, electrons that are flowing away from this negative polarity that we've got here, and they're flowing in that direction. So we've got the electrons flowing in this direction, right? That's my electron flow. I hope you're getting all this down. You're getting a fantastic lecture. Where's my other color that I've got here? Do I have a purple? Oh, the purple never worked, did it? I got a couple browns. Oh, let's see what this color is. It's black. Okay, and then the current is going in this direction, sort of a gray, right? So my current is going in that direction, and the electrons are going in the opposite direction. So as soon as I throw that switch, even though I've got a capacitor in here, I still get current flow. Oh yeah, as soon as I throw that switch, the capacitor acts like it's not even there for the first instant, the first millisecond, the first microsecond. It acts like I've got no capacitor there, and I've got a short-circuited wire right across that capacitor. I thought I'd just throw that in. We're getting a little off track. Let's get back to capacitance. So, charge. We know that charge is a coulomb, and we know that that is an amp second. And what's voltage? We know that voltage is a kilogram meter squared per seconds cubed amp, right? Well, let's just simplify that in our heads, because you're engineering students and sophomores, and you know what you can do. And you know that we've already taken the numerator times the reciprocal of the denominator, so we get an amp squared seconds to the fourth over a kilogram meter squared. And what do we call that? We call that a farad, after Michael Faraday, the great British scientist and experimenter. And so that's capacitance. Just a second. Where is that? I thought somebody was at my front door, but I guess not. Anyway, so that's a farad, and that's capacitance. And so what I want to do next is I want to talk a little bit about magnetic fields. But I also want to catch up on a couple things. Before we do that, let's look at pressure. You know, pressure, if we define an equation, it's really force per cross-sectional area, isn't it? Force per cross-sectional area. Well, we know that force is a kilogram meter per second squared, and we know cross-sectional area, is meters squared. Sorry about that. I was thinking of the next unit that I'm doing while I'm doing this one. Getting a little bit ahead of myself, so let's just, if we multiply the denominator or the numerator by the reciprocal of the denominator, what we end up getting is a kilogram per meter second squared. And we actually have a nickname for that unit. It's called the Pascal, and we usually write it as a PA for pascals. Yeah, I've never really seen just the P all by itself. I suppose that would represent something else. I don't know. But we use PA for Pascal. Might as well write it out there. I actually named my son Pascal, but not the same Pascal. It actually is Paschal, after the patron saint of Paris. And I don't know why that says T. Oh yeah, that's because that was a negative, wasn't it? Okay, so that's a Pascal. Now, when I say pressure, this could also represent stress, because if we looked at, let's say, a tensile specimen, a piece of steel or a piece of aluminum, and we were pulling on that aluminum with a force, right? Let's say that we've got something like 10,000 newtons, right, that we're pulling on it with, and then we look at the cross-sectional area of that, we can actually do the same thing. We could say that strain, and we usually use sigma for strain. Strain is equal to the force in that solid piece of steel, right? That's steel, divided by the cross-sectional area. When we're looking at pressure, we're usually looking at like a fluid or a gas. I really should say fluid because that includes both a liquid and a gas. So we're looking at a fluid that's pushing on a cross-sectional area, like let's say the water on the bottom of a dam gateway. And when we're looking at this, we're looking at what the tensile forces are inside of a piece of steel. I'll just write steel over this. This is more the solid mechanics, whereas pressure is more for fluid mechanics, if you know what I mean. And so we get the same thing here. We get pascals, right? Now, what is a pascal really? A pascal is really energy per volume. And that's why I named my son Pascal, because he's really energy per unit volume. Yes, I know. Don't be the son of an engineering professor. There's the moral of that story. Although my son loves his name, and his nickname is Pass, and he's a great soccer player, so that's all good. All right, so energy then is kilogram meters squared over seconds squared. And then volume is meters cubed. You see what I'm really doing here? I'm just teaching you how to use these. All throughout your life, you're going to be doing this with units and stuff. You're going, God, I think that has, the heat that's coming out of that cup has to do with the thickness of the cup. And someone's going to say, no, it doesn't matter how thick of ceramic that cup is. Heat comes out just as fast. You go, no, I think the thickness of the cup is slowing it down. If I make that cup twice as thick, it'll be half as fast. And of course, I'm talking about the conversation that the people had that actually figured out what heat transfer was all about, right? So let's go back to this now. Now this is cubed, and we get the same thing, kilogram per meter second squared. So yes, energy per unit volume is the same as pressure, is the same as strain in solid mechanics, is the same as pressure in fluid mechanics. They're all the same. It's energy per unit volume. All right, so I got that out of the way. The next thing that I wanted to look at is flux. Now, before I do that, I just want to look and see, and sort of have a discussion. Why don't I have that discussion of flux in the next one? I'm going to continue presenting these. So magnetic flux, right? Magnetic flux is, well, let's say voltage times time. I just want to get this out. And what we'll have a much longer discussion of what magnetic flux is later, but just to talk about the dimension and the units of magnetic flux, well, we've got voltage, which is kilogram meters squared per seconds cubed amps, times time, which is just a second. So that gives us a kilogram meters squared over seconds squared amps, right? Now, what do we call a kilogram meters squared over a second squared amps? We call that a Weber. Yep, it's named after a barbecue grill that we use. No, of course it's not. But that is what we do. That's and what am I talking about here? I'm talking about magnetic flux. And we'll have a much more in-depth discussion of magnetic flux at the end of the, I shouldn't say the end, about the middle of the lecture series, all right? Now, the next thing I want to look at is something that you're more familiar with, and that's magnetic flux density. And what that is magnetic flux per cross-sectional area, right? We want to know the amount of magnetic flux that's flowing through things. Let's say that I had a bar magnet right here, right? And this is the south end, and this is the north end. Well, I have flux that's going to be flowing out of the north end into the south end. I'll just put some arrows here as to the direction it's going, right? So we've got flux that's flowing out and I think that everybody can see that if I was to take a cross section right here, I'm going to have a lot more flux lines going through it than if I take the same size cross section out here, right? So I'd have a lot of flux density here, and I'd have a little flux density here. And that's what magnetic flux really tells us. So flux density really tells us where the heat is really where the magnetism is really intense. Where is the magnetic strength the greatest? And of course, it's the greatest right here, not out here in the middle of the flux lines. So when you look at that, it'd be over the square. So this would be kilogram meters squared over amp seconds cubed divided by meters squared. I think everybody can see that that gives you a kilogram per amp seconds. Oh, did I say cubed? I'm sorry. I meant seconds squared, amp seconds squared. So there we go. So kilogram per amp second squared. And we have a name for that too. In fact, that is something that we use even more often because we talk about the magnetic field at the surface of the Earth, and this would be a Tesla, right? Now, what is the magnetic field at the surface of the Earth? The magnetic field at the surface of the Earth is about 50 microtesla. That should be a 5. 50 micro, boy, that doesn't look like a good 5, does it? It's 5. 50 microtesla is the terrestrial, is the magnetic field of the Earth. And we talk about the magnetic field of the Earth in flux density terms, not in flux terms. We don't know, I don't know what the overall flux of the entire magnetic field of the Earth is. It's got to be quite substantial, I'm sure. I'm sure somebody at NASA does know what the answer to that is, but I don't. The last one that I really want to look at is inductance. And what inductance is really flux per amp, right? Flux per amp. And so if we do the math there, kilogram meters squared over seconds squared amps, and we divide that by an amp, right? That's going to give us a kilogram meters squared over seconds squared amp squared. And we have a name for that. That's the unit of inductance, or the dimension of inductance. And the unit of inductance, of course, is a Henry. Yep. And so that ends the dimensions and units part of the course. I could get into so many other things, and we're going to definitely talk more about capacitors and inductors, how inductors store energy, how capacitors store energy, all of those things all throughout the course. But what I wanted to do, or I shouldn't say, you know, in the Network Theory 1 course. In the mechanics course, we're going to be concentrating more on this, which is the steel and the pressure and all of those things. However, you know, all of this is important for your general understanding of engineering, dimensions, and units. And you also will be working with other engineers from other disciplines too, and you'll want to understand, you know, pressure. Don't say, oh, I don't want to understand pressure because I'm an electrical engineer. No, you want to understand the units of pressure. All of these things intertwine all the time. So, you know, focus on that. All right. I'm going to end this lecture here now. This is our third and final lecture on dimensions. Then we're going to start getting into the meat of the course.